These are the notes for Algebra 2, Section 2.7, pages 122 through 126 in your textbook. They have to deal with absolute value functions. An absolute value, to just review briefly what it is, essentially makes a number positive. For instance, if I were to take the absolute value, that's what these two lines mean, the absolute value of positive 2 would be positive 2. But the absolute value of negative 2 would be positive 2. So a number that is negative becomes positive, and a number that is positive stays positive. That means that the absolute value of a number is a positive number. The absolute value parent function is defined as f of x, the function of x, is equal to the absolute value of x. So if x is 1, then the absolute value of 1 is 1. If x is negative 3, the absolute value of x is 3, so on and so forth. Now we want to look at the parent function first. And here we have a graph of the parent function. There are a couple of things that we want to note. The first is the vertex. Now the vertex is the lowest or highest point of an absolute value function. On the parent function, the vertex is at 0, 0, right in the origin. We're going to use that a lot when we start doing translations because we're going to begin with the origin. As we can see, from the vertex we have two lines going in opposite directions. On one side I have a line moving up and to the right, and on the other I have a line moving up and to the left. If we were to look at the slope of each of these lines individually, we would see that this line moves up 1 and over 1, which means that the slope of the right side, the right line of the parent function, is 1. And that is m. m equals 1. On the other side, if we were to do the same test, we would see that the slope of this left side moves down 1 and over 1, meaning that the slope of the left side of the parent function is negative 1. And that's the way the absolute value functions are all going to look. We're going to have one slope that's positive and one slope that's negative. When we're dealing with absolute value functions, we want to talk a lot about translations and transformations. I have a graph of a translation here. A translation moves the graph, but it does not change the size. As we can see in our picture, I have my parent function in red, going through with the vertex at the origin, two slopes, one of 1 and one of negative 1. And I have a new function. The new function has a vertex at 2, 1, the point 2, 1, and it still has slopes on either side of 1 and negative 1. Since the slopes didn't change, the graph is still the same shape. So we have not changed the shape of the graph, we've only changed its location. Now, the graph of the absolute value of x minus h plus k is the graph of the parent function y equals the absolute value of x, translated h units horizontally and k units vertically. So when we're looking at the equation of an absolute value function, we can tell how far it moves left and right by looking at h, and how far it moves up and down by looking at k. Now, in our example here, if I start from my vertex, which is where I always want to start, I can see that my graph moved up 2 and to the right 1. That means that my h value is 1 because it moved to the right 1. My k value is 2 because it moved up 2. that would make this equation y equals the absolute value of x minus 1 plus 2. Alright, we might be given a graph and asked to, or given an equation and asked to graph it. If we are asked to do that, the process is can be fairly simple, or it can be a little bit more complicated. Since we're just dealing with a translation right now, we're not changing the shape of the graph. All we need to do is look at h and k. In this case, I have x plus 4, the absolute value of x plus 4 minus 2. Now, according to the formula that we had seen before, we have y equal the absolute value of x minus h plus k. What that means for us is that anytime we're looking at h, we need to change the sign of the number in the equation, because our formula is negative h, minus h. That means our h value is not 4. We have to change the sign to make it negative 4. So h is negative 4. K is minus 2. Now our formula says it's plus k, so it's going to stay the same. It's going to be minus 2. K is minus 2. So we've got our horizontal movement minus 4, and we've got our vertical movement minus 2. We start with what our vertex would have been, which is the origin if it was the parent function. From the origin, we move backwards 4 for the h movement, and we move down 2 for the k movement. And we end up with a new vertex at the point negative 4, negative 2. And in fact, we can always find the vertex by referring to it as the point hk. Right, from here, we know that this is just a translation because it fits this translation form. What that means is we just need to draw the lines. And our slope on the right side should be 1. That means we're going to go up 1 and over 1, 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 so on and so forth. So I'm going to draw a line with the slope of 1. And there is my line. I can see that my slope goes up 1 and over 1, up 1 and over 1. The slope on the left side will move down 1 and back 1, or down 1 and forward 1, or up 1 and back 1. The important thing to keep in mind about the left and right sides of your absolute value function is that the equation should always graph a V. The V might be wider or narrower, it might be upside down or right side up, but it will always be a V kind of shape. That means that if I'm graphing my lines and I get something that is not a V kind of shape, I did not graph it correctly. Here I have one side and the other side would continue up this way. That is a V shape. So I know that I graphed it right. When we're dealing with transformations, which are what we call a change in the equation that actually changes the shape of the graph, for absolute value functions, we're looking at the absolute value of a. And our equation would normally look something like this. Y equals a absolute value of x. Here we can see it. Y equals a absolute value of x. We look at the absolute value of a. So whatever a is, if it's negative, we make it positive, so on and so forth. If the absolute value of x is not 1, the graph of y equals a times the absolute value of x is either stretched or shrunk vertically, depending on the value of the absolute value of a. If we find the absolute value of a and it's bigger than 1, so if it's 2 or 3 or 4 or even negative 2, negative 3, negative 4, then the graph is vertically stretched and it will appear narrower. It will look narrower. If the absolute value of a is less than 1, but it still has to be positive because it's an absolute value, so we're looking at numbers like 1/2 or 1/3 or 3/4, something like that, then the graph is shrunk or appears wider. So essentially, if we have a whole number in front of the absolute value of x, we have a narrower graph. If we have a fraction in front of the absolute value of x, we have a wider graph. And we'll see how that works with a couple of graphs. And we're not translating this because this doesn't fit that translation form, but we are transforming it because we are multiplying the absolute value of x by 3. Our vertex is going to be in the same place it always is, but this time my graph is going to be narrower. And this is actually not that bad. I know that a is 3. I know that it's going to be narrower. One side of my graph is going to be moving upwards at an angle. The other side is going to be moving upwards in an opposite angle. So the way I want to think about this is to imagine a to be the slope of my line. So since a is 3, I want a line that is 3/1. So from my vertex, I move up 3 and over 1. I have a couple of points. From my vertex, I will draw the line that connects those points. That is the right side of my absolute value equation. On the other side, since the parent function had a slope of 1 and a slope of -1, this function is going to have a slope of 3 and a slope of -3. So that means we could graph another point by moving up 3 and backwards 1. So this would be another point in my absolute value function. I will graph the line that connects those 2 points. And we can see that my graph is a V shape, so I know that I graphed it correctly. It is narrower than the parent function because it has a steeper slope. All right. If we have an a that is negative, then the graph of y equals a times the absolute value of x is reflected along the x-axis. So if it was pointing upwards, now it's going to be pointing downwards. Typically our graph would look something like this. But if we have the absolute value or y equals -a times the absolute value of x, then that graph is going to flip upside down. That means that the slope that was positive is now negative. The slope that was negative is now positive. So it kind of swaps around. And we'll see how that actually works out for us. I'm going to graph y equals -1/2 times the absolute value of x. There's no translating going on here because it doesn't have the translation h and k. So my vertex is going to stay at the origin. But I am multiplying x by -1/2. Since it's negative, I know that my graph is now going to be opening downwards. It's going to be reflected along the x-axis. Since a, the absolute value of a, is 1/2, because the absolute value of -1/2 is +1/2, I know that my graph is going to be wider. Now, as in the last example, we can use a as though it were the slope of a line. But we have to think about it a little bit differently. Normally, if this was just +1/2, we would move up 1 and over 2 for the right side, and then up 1 and backwards 2 for the left side. But since it's -1/2, we have to go the opposite way. We start by moving downwards 1 and over 2 for the right side, and we can graph that line. Now notice this is actually the slope A equals, or this is actually if the slope was negative 1/2. We move down 1 and over 2. On the other side of the absolute value sign, we change this negative to a positive, so we get a positive slope, and we have down 1, backwards 2. Down 1, backwards 2. This is a positive slope, so I draw the line that connects it, and this is where I end up. As we can see, it is a V shape. It's an upside down V shape, but I was expecting that because A is negative. The slope of one side is negative 1/2. The slope of the other side is positive 1/2. All right, we want to do an example where we're combining all of these things together. Now, when we're going to attempt this on our own, pause the video and graph the function. Keep in mind this is negative 1/3, so A would be negative 1/3, but we also have the translations. We have an H and we have a K. H, we have to change the sign. K, we don't. So we're going to have a new vertex, and we're going to have a shrunken graph, so a wider graph that is reflected along the x-axis. So we need to combine all of the different things that we've looked at to get one graph. Pause for a moment, pause the video, graph the function, and then unpause the video and we can see how you did. Alright, when I graphed this function, this is what I got. I knew that A was equal to negative 1/3. I knew that H was the opposite of 2, so it's negative 2, and K was negative 1. That meant that my new point, my new vertex, was at HK, which it is. Negative 2, negative 1 is the point right here. From there, my slope for the right side of the absolute value function is negative 1/3. So I moved down 1 and over 3, down 1 and over 3. And I had points here and here. The left side of my absolute value function is the opposite sign, is the opposite of 1/3, which is negative 1/3, which is positive 1/3. So this is a positive slope. I moved down 1 and backwards 3, which I am allowed to do. So I ended up with a graph that is wider, but it is still in a V shape. And your graph should look the same way.